Greetings, Earth and Space Explorers. I'm Bill Waller, host of Doc Waller's Earth and Space Reports, coming to you today, which is November 9th, 2020, to give you some ideas for doing astronomy activities that you can do both indoors and outdoors. And so I'm going to get started with this PowerPoint by sharing my screen. Here we go. And let's just get going. So I call this lesson, if you will, experiential learning opportunities in astronomy and astrophysics. And you can learn more about it by going to my Science Gazette site. It's Dr. Waller's Science Gazette. Or you could just start looking outside. Here's a great view of Starry Sky from the north in Canada, which shows some aurora. And maybe some of you got to see this during the summer, Comet Neowise. So astronomy has a lot going for it. It's a very visual science, but still it leaves some things to be desired. There we go. Okay, and here's the conundrum. In astronomy and astrophysics, the entire cosmos is our laboratory, which is pretty neat. It's far out. There's a lot of material out there, luminous material out there, which is very alluring. There's a lot of concepts which are really exciting to think about, black holes, big bangs, all that. But it's also very intangible. And you can see that in this lovely picture by Marcin Zajac of the New Mexico Badlands. That's where he took it. The tangible can be seen with this beautiful rock formation. It's known as a hoodoo. It's been sculpted by wind and rain. And you could touch that, at least that's tangible. And maybe the sun setting in the distance, maybe you felt its warmth during the day. But then after that, everything else ends up being pretty visual. You have Jupiter here, and then Saturn there. And then there's this Milky Way, this beautiful diaphanous Milky Way full of star clouds, nebulae, which are caused by stars illuminating their surroundings, their nebular surroundings. And then, of course, the darker nebulae, which are due to dust, clouds of dust obscuring the starlight behind them. All this, of course, requires a very dark sky. Most of the skies that you and I get to behold is not nearly as dark. And so we might only be able to see the setting sun and Jupiter and Saturn if we're lucky. So intangible and in many ways not seeable for many of us. So how can we better understand all of what's going on in the cosmos, all this cosmic commotion, if we cannot touch it and many times cannot see it? Another way of asking this same question is, how then can we make the intangible more tangible to be more experiential and therefore comprehensible? And you can do this in basically 4 different ways. You can make models and interact with those models. We humans are very good at making models and representations of what we think is going on. There's the mental models, including drawings on paper, animations, etc. We can do that. Physical models like globes that you can touch, a rough surface that you can touch, representing, say, the surface of a planet. There's also motion, kinesthetic models, whereby you could literally dance the phenomenon, such as spinning and orbiting. And then also sonic, where you can represent, say, a spectrum or a light curve over time, which would be hard to interpret otherwise. So those are the models. You can also work with hands-on simulations. I'll show some of those, and online interactives as well. You can literally carry out research, cutting-edge research, through online citizen science research platforms such as the Zooniverse and NASA at Home. These are crowdsourcing research projects whereby your input is combined with other folks' input, and you can do stuff which leads to new and exciting research results. Finally, since astronomy in many ways is an observational science, it's less of a laboratory science, you can make, record, and analyze astronomical observations. Beginning naked eye, just that scene with the comet and the aurora, that's an obvious naked eye sight. But then you can use your binoculars and telescopes that are available to you. And then finally, these days, you can use archival databases, which are just getting better and better. So I just, here's my plug. I'm working on a book. It's called Astronomy, A Beginner's Guide Through Space and Time. The text is all done, working on the illustrations now. But in writing this book, this has led me to articulate 23 teachable moments in astronomy and astrophysics. And again, you can find them in Dr. Waller's Science Gazette. And now I'm going to start talking about them by scale. Begin with the Earth and sky. And a simple question, how do we know the Earth is spinning? How do we know the Earth is round is one question that is definitely worth asking. But once you have a feel for how we know that, how do we know the Earth is spinning? Many people will say, oh, it must be spinning. That's why everything rises and sets in the sky. But that's just an explanation for that phenomenon. It could be the other way around, that that stuff is actually going around the Earth instead of us spinning underneath all that stuff. And so that can lead to ideas of the Coriolis force driving wind patterns eastward as they go to higher latitudes. It can lead to the Foucault pendulum, which is an inertial system, and the Earth spins beneath that inertial system, and you end up getting the Foucault pendulum moving with respect to the Earth. There's other reasons that you can talk about, and there's some red herrings as well that are worth talking about. Can you dance like the Earth? Well, the Earth both spins, and it spins around its axis, but it also orbits around the sun, like all the other planets. And that combined motion leads to some interesting results. If you model it in the classroom with some central object serving as the sun, and then have your students spinning around and orbiting at the same time, you will find that you have to spin around a little bit more than once around in order to get back to the same configuration with respect to the central object, the sun, representing the sun. And that is a way for you to understand that the solar day is 4 minutes longer than the sidereal day. That also leads to why the sun is in the direction, different directions in the sky as you spin and orbit around. Visualizing lunar phases. Sometimes many students think that the phases of the moon, once they start noticing the phases of the moon, are caused by shadows on the moon. And so that is something that you might want to try to confront and break. And one way is to consider just theatrical lighting, say of the Beatles here in their very first album in America. And you can see that they are lit like, they kind of look like the moon, first quarter moon phase. And it's pretty obvious if you ask your students where the illuminator is for this particular picture, they would all say that the illuminator must be over here, shining on the side of the Beatles' faces. So that introduces the concept of theatrical lighting, if you will, having to do with where the moon is with respect to the illuminator as seen by us. And then you can move on to an activity. It's very old now, but it's a very reliable activity by having orbs. In this case, they're oranges on forks, but you could also use larger orbs, grapefruits, or soccer balls, volleyballs, basketballs, pretty smooth orbs. Tennis balls are right out, don't work. I tried it, failed. But basically, you have an illuminator basically out of the picture in the foreground shining on these students, and they're going to have to spread themselves out, but they basically have the moon, their orb representing the moon in front of them, and they move the moon around them, and they will find that their view of their representative moon will change in its phase from crescent to first quarter to fully illuminated, and then back to last quarter and waning crescent. They can simulate all those. The aha moment comes when you do this outside with the actual moon and your orb. You go outside during a morning where you have a gibbous moon or a last quarter moon, and you point your orb towards the moon and make sure that your orb is illuminated by the sun, and you will find that the orb has the same phase as the moon. Aha. So visualizing lunar phases, there's lots that you can do there. Full tilt modeling of Earth's seasons. Again, this is a kinesthetic activity where you're basically incorporating the tilt. This is kind of reminds me of a Mr. Natural. You're tilting and going around at the same time. Well, let's see, I got the hand. And so you have a tilt, or I'll have the tilt like that. And you maintain that tilt with respect to a particular wall, say indoors, and then start going around a central object, and you will find that your tilt with respect to the central object, namely the illuminating sun, changes. And so at least you can get started understanding why there are seasons based on the changing tilt with respect to that central object, that illuminator. Solar system. If the sun was a grapefruit, walking a scale model solar system, you will need some way to measure your distances. One way is a big tape measure. Another way is to get one of those digital measuring wheels, digital measuring wheels. Those work really great. But you can actually do a true scale model solar system whereby both the relative sizes of the sun and planets and their relative distances are correct. And on the National Mall, there is such a scale model solar system, and there are others elsewhere in the highways of Maine and elsewhere. But I find that a grapefruit is probably the smallest scale that you can use so that you can get out to Neptune on a very large playing field. And so if the sun is a grapefruit, then the Earth is a poppy seed, only 10 meters away. And the Jupiter is a big blueberry or a Kix cereal, a full 50 meters away. So that's half a football field. Saturn is an allspice, and that is 100 meters away. So that's the length of a football field. And you can get out to Neptune, which is a peppercorn, about 300 meters away. So this is a fun scale model, and there is a big takeaway from it because you will see, literally see and feel, having walked it, that the inner solar system of Mercury, Venus, Earth, and Mars is much, much cozier compared to the outer solar system, which is so much more spread out. And that's a great way to get a feel for the solar system. Sketching the moon. This can begin naked eye, especially with kids who have trouble looking through eyepieces, either in binoculars or in telescopes. It's best to start naked eye, and perhaps you will be able to see what they see on the moon. And if they have pretty good eyes, they might see the Maria, the lava beds on the moon, for example. Here is an example of what you can see through a telescope during first quarter phase. This is the break between the night side and the day side when the relief is best. This is what a good amateur astronomer can see through a telescope. Simulating how the moon got its craters. This can be done starting with a big cookie tray, put a layer of sand down, put another layer of flour down, and then another layer of chocolate powder, cocoa powder down, and then start dropping objects like marbles, etc., onto this layering of material. And you can end up getting nice craters with even ejecta rays, which are seen in the large craters of the moon. What you won't see, what you will see, I'm sorry, you can get elliptical craters as well if you throw your object at an angle onto the tray. These are not seen on the moon. They're always circular craters, and there's a reason for that, having to do with the impact energies and the explosive properties of the impactor. The impactor ends up blowing up, and that leads to what we would say very symmetric explosions on the moon, and hence invariably circular craters. Exploring the planets in history. Here's where planetarium software works really well. Stellarium is the one that I use. And you can go back in history and see the configuration of planets with respect to the stars back in the day. One really good one is to understand how the planet Neptune was discovered in the first place, and that's because it was very close to Uranus early in the 1800s. Uranus was lapping Neptune early on, and you can go back to that date where those perturbations were first noted, and then see how that propagated to a prediction where Neptune would be, and its ultimate discovery later on in the 1800s. You could also explore the configuration of the planets during the time of Christ, which is one possible explanation for the star in the east. You can also explore what was going on with Columbus in the Caribbean when he ran into a rather hostile tribe of natives, and he barely got out alive thanks to his prediction that he was going to darken the moon. And so lo and behold, there was a lunar eclipse that he knew about, and it happened, and that was enough for him to escape death by the hands of those natives. Building a model comet, there are recipes which I refer to. Basically, a comet is a dirty snowball, and it consists of water ice, yes, but also dry ice, CO2 ice, plus an admixture of dust grains and organic molecules, and so they have a pretty awesome recipe for this, and you can start making what would be the nucleus of a comet. They tend to be very, very dark, and so you have to get your recipe right. Galactic, so we're moving out beyond the solar system here, starting with the stars, and for some of you, they'll be able to look up and see stars, your students, and if they can see stars, they'll notice, or might be able to notice, that the stars have different colors. The colors are pale, and that has to do with the spectral energy distributions, which can be discussed. The stars have many colors, but they are brightest in a particular color. And so that dominates the overall color of the star. Those colors map to temperatures on the surfaces of the stars and corresponding luminosities as well. And this can be vivified by using a stovetop or a hot plate and changing the current that goes through those heating elements, beginning with a dull red at low temperature to a warmer temperature, which has a brighter orange, and then orange yellow. That's about that's about as far as you can go with a stovetop. But then you can discuss welding torches, and they can get to even higher temperatures and bluer colors. And so the mapping of color to temperature from red to blue, from cool to hot, can be vivified this way. In the meantime, you also notice that as the colors change, the brilliance also increases tremendously. And that's another way of showing the Stefan Boltzmann law of intensities from black body objects, black bodies. Finding exoplanets, a citizen science activity. This started out on the Zooniverse platform and making use of the Kepler mission, the Kepler telescope data, which has to do with monitoring stars and their light output. And as a planet gets in front of a star, it will obscure a little fraction of the star's light. And so you will see a dip in the light profile. And they provided a good interface for you to explore a variety of stars that had been recorded by the Kepler satellite, the Kepler mission, and new discoveries were made by the citizen science. So that's something that you can do. I had one student do it with some pretty positive results. They've moved on since Kepler to now TESS, so new data are streaming in to this activity, finding exoplanets. Exploring stellar and nebular Milky Way, a citizen science activity. Again, the Zooniverse platform is a great place to do galactic research. And my favorite was the Milky Way project, which basically made use of infrared images from satellites of the Milky Way. And you were asked to delineate bubbles that had been blown by various processes. Those processes could include the ultraviolet light blasting away from a hot newborn star, or it could be the winds from that star also blowing the bubble, or it could be an explosion, a supernova explosion after this star went through its short life. And but there are always new projects coming on board, the Zooniverse and I suppose NASA at Home project as well. So I recommend that you check that out. Walking a scale model Milky Way. Here is another outdoor activity. I recommend doing it. There we go. I recommend you doing it on a sidewalk, and it would extend for around 300 meters as well. Bring colored chalk, and you can delineate the objects that you encounter along the way, starting at the sun and going towards the galactic center. This is an artist's rendering. You will end up, well, at the sun, there's the solar neighborhood very quickly, and then there's the Gould's belt of bright stars you could get past. And then once you hit the first spiral arm, there's all sorts of star-forming nebulae that you encounter, and you can draw them on the sidewalk to scale, which is pretty neat. And then finally, you get to the galactic nucleus, and with all its excitement going on there with the supermassive black hole. And there's also globular clusters along the way, the oldest objects in the universe, these dense balls of hundreds of thousands of stars. And you can go in the other direction and pass through another spiral arm, which has its own assortment of star-forming regions and newborn star clusters, such as the double cluster in Perseus. So that's a fun outdoor activity. Extragalactic, beyond the Milky Way, starting with the local group of galaxies. This is something that you don't have to do outdoors. You can do it indoors. And the reason is that the spacing between the galaxies, like the big galaxies, the Milky Way and Andromeda, the spacing between the galaxies is much less compared to their sizes than the spacing between stars. The spacing between stars is 50 million times greater than the sizes of the stars. If the sun was a grapefruit, the next nearest star, Alpha Centauri, would be somewhere about 1,500 miles away on Earth in that scale. But here, you could have the two galaxies, let the Milky Way be 10 centimeters in size, the size of 3 CDs stacked together, maybe with a cut-up Twinkie to represent the central bar. You've got yourself a Milky Way. About 25 or is it 2.5 meters? 2.5 meters away is the Andromeda Galaxy, okay, on the same scale. And that's because they're only about 25 times larger, sorry, 25 times more distant than they are large. So you can fit it into a room. 2.5 meters is not so bad. So the Milky Way, 3 CDs stacked together with something representing the central bar. You can draw on the disks to make the spiral structure, as best we know. The Andromeda Galaxy, again, 3 CDs with maybe a tennis ball cut up to make the bulge. It doesn't have a bar. It has a bulge of stars. And then the Triangulum Galaxy, Messier 33, that would be a mini CD with no bulge or bar, and it has its own spiral design, a ratty spiral design. And so you could have students draw those things. And then there's all these other dwarf galaxies, much smaller galaxies, could be represented by cotton balls or whatever you have handy. And finally, you could hang all of this from the ceiling to make a 3D model of the local group of galaxies. Classifying galaxies according to their shapes. There's one activity which I refer to that has your students devise your own classification system for the galaxies that are presented before you. So that's kind of neat. But then you can move on to the classification system which has been accepted, the Hubble-based classification system of spiral galaxies, elliptical galaxies, barred spiral galaxies, and irregular galaxies according to their shapes. And you can do your own classifying. And there are opportunities to do that online. Exploring galaxies with active nuclei, the Fermi Gamma Ray Telescope group, along with the Sonoma State University Science Education Group, have got together and put together some rather nice online activities, up to and including making a physical model of an active galactic nucleus, including the accretion disk and the jets that are spitting out of it. Exploring the Coma cluster of galaxies. Once you get your galaxy classification chops up and running, you can then apply them to the Coma cluster of galaxies, where you will see differences in the types of galaxies that are present in the cluster as a function of where you are in the cluster. The inner regions has a lot more elliptical galaxies, very few spiral galaxies. The outer parts, you get more and more spiral galaxies. And so that begs the question, why? What would produce that sort of segregation? And finally, we have on the extragalactic scale, tallying all the galaxies in the observable cosmos. Yes, you can do this. And that is available, I think, in Amazing Space website. It's a NASA website, whereby they present to you the Hubble Ultra Deep Field of galaxies. And then you're asked to pick a small region of that field. So the field's already a very small fraction of the sky, but you're asked to designate a particular subsection of that field in which you can count, literally count all the galaxies that you see. It's doable. And once you've counted all the galaxies you see in that subfield, then they provide you with the magic number which compensates for the rest of the sky. And invariably, you will end up estimating between 50 and 100 billion galaxies observable in the cosmos. So that's a pretty neat one. Cosmic consequences, modeling the cosmic expansion. Many of you know that galaxies are receding from all other galaxies in one big expansion. Basically, the universe is expanding and taking the galaxies along for a ride. The space-time is expanding and causing the universe to stretch out. And so you can simulate this with analogies using a rubber band, with marks on the rubber band, and you'll find that once stretched out, that the marks will be more spaced out, and that if you refer to one particular mark as your reference mark, like our Milky Way galaxy, you will see that the farther a galaxy or another mark was initially, the more it will have stretched. The farther a galaxy is, the more it will have stretched. That's basically Hubble's law of universal expansion. That's a one-dimensional analogy. Two-dimensional analogy, you could use a balloon and with marks dotted on the balloon for the galaxies. Blow it up, and you will again find that if you refer to one particular mark, the more distant marks initially will have displaced the most away from that initial mark, that reference mark. And but that implies a closed universe, like a two-dimensional analogy of a 3D universe, and that doesn't seem to be the case. So I prefer getting a stretchy piece of fabric and attaching like rulers, straight edge rulers to the edges of the fabric, and then stretching out in X and Y. And if you have sequence on those on that stretchy piece of fabric, you will again find that the farther sequence will have displaced the most after stretching. So, okay, so that's modeling the cosmic expansion. How to form stellar and planetary systems, a playground activity that involves a carousel, if you can get access to a carousel, and it also involves conservation of angular momentum, such that when you have something spinning, say the carousel, and you start moving in, bringing stuff inward, which has mass, so bring some weights with you. As you go in, the carousel and you will spin up, but it spins up too much. Stars in formation don't spin up as much as would be predicted. And so what is preventing that huge spin up is you have to get rid of some of that angular momentum, which was conserved, bringing it in, but now you have to get rid of it somehow. Stars do it with jets, but you can do it by tossing your weights over the side and thereby slow down your carousel. So that's something to play around with, literally. Why black holes are not ravenous sucking machines. This can be done with a vacuum cleaner, and you can see that the range of action around the nozzle is actually very limited, and that's analogous to what we have with black holes. Their ravenous ways are highly constrained spatially, such that you have to start with the initial star, which collapsed to a black hole. You'd have to be well inside the initial radius of that star to start seeing warped space-time and all the consequences. So that's a good analogy for black holes, rather noisy. Recipe for representing the universe in a jar. Yes, you can represent the whole universe in a jar according to its principal components as we know them best today. Starting with the luminous matter, that could be some glitter. And then you have the non-luminous ordinary matter, that could be some salt. And non-luminous exotic dark matter, that could be sugar. And then, of course, non-luminous dark energy would be the water that you have in the jar. And you put all that stuff together, the salt, the sugar will dissolve, disappear over time. And then what's left is basically nothing except for the glitter that you can see. And you can illuminate that glitter with a lamp and stir it around. And just imagine what the universe is doing. How would you communicate with alien intelligences? And so this is the last one that I articulated. And it's a big challenge. We don't really know what alien intelligences would be like. We don't know what sensory organs they might have. Would they see better, smell better, hear better, or other senses that we know nothing about? Would they be radio receivers, for example, organically? And so this challenge motivates you to ask your students to consider the plaques that were put on the Pioneer spacecraft and Voyager spacecraft that went to Jupiter, and then for the Voyagers, Saturn, and beyond. Um, this plaque in particular shows basically how to play the record that is contained within. That record contains images of Earth and sounds of Earth, all kinds of different sounds. Um, and it shows how you need to play the record, both with the turntable, and that the signals will correspond to sounds and sights. Here is, I believe, a representation of the solar system and the hydrogen molecule. And so this was an attempt, one of several attempts to communicate our existence and our civilization to aliens. So what would you do? Here's an example that I had some participants do during a commemoration of the blue dot, the big blue dot, pale blue dot, 30th anniversary, where Voyager looked back and saw Earth as just this tiny little blue dot in the darkness of space. And so there's a person representing, I guess, peace and love, that using English letters and something to represent life, I suppose. Here's a person a little not so sanguine, providing SOS, what could be interpreted as SOS. Another person providing a digital sequence of digital numbers and a waveform. And another person who starts with a human, close-up of a cell, close-up of the DNA strands. That person is part of a planet Earth. Earth is part of a solar system, and the solar system is part of a galaxy. Okay, so this is a fun challenge. Presuming that there are alien intelligences, how the heck would you communicate with them? Okay, I promised that there would be some information about observing. The Archival Observing is getting better and better, beginning with NASA's Skyview Virtual Observatory, where they have all sky databases at multiple wavelengths, from the radio to the infrared and the visible or optical to the X-ray and the gamma ray. These are magnificent databases. You can plot these sorts of maps. You can choose a galactic coordinate representation, for example, and all sky, where you have the center at the center of the galaxy. Here we go, near the center of the galaxy visibly. And you go up 90 degrees to the galactic pole, and down 90 degrees here, and then over here at 180 degrees, and then 180 degrees back to the center. This is all possible. You can do these all sky maps. You can do a small section of the map at multiple wavelengths, overlay them, etc. The Virtual Astronomical Observatory also provides even more data on any direction in the sky, basically on any object. And then there's Microsoft and now the American Astronomical Society's Worldwide Telescope, which provides a very slick interface for exploring the sky at multiple wavelengths. And it also provides abilities to zoom in and make animations and narratives, so that you can make your own shows. So that's worth checking out if you're interested in making shows. Okay, archival observing. Remote observing. I would recommend you start with observing with NASA, that's OWN, and they have these small telescopes in various places, including in Cambridge and in Arizona, and you can get on in the queue for free, especially if you're in an educational institution, and you can order up an object and ask that it be observed for a certain length of time. They give you options. You can observe through red, green, and blue filters if you want to make color images, which they have the software for enabling you to do that. And so I recommend starting with that. And once that whets your appetite, moving on to something in the Las Cumbres Observatory Global Telescopic Network. And they have bigger telescopes, which can be accessed to make imaging observations, including the Fox telescope, which is a big telescope on a big mountain in Hawaii. That's pretty awesome stuff if you want to get involved. I think you have to be affiliated with an educational institution. SLU is something that anybody can access for a fee. To get started, it's around $50. And you can not only specify the observations that you want, but you can actually get live views as the data starts accumulating. So pretty neat stuff. Remote observing. Hands-on, eyes-on observing, of course, can't be beat. So get thee to an astronomy club. Get to know your astronomy club in your area. There's quite a few of us around. I'm a member of the Gloucester Area Astronomy Club. Nearby is the North Shore Amateur Astronomy Club and the Amateur Telescope Makers of Boston, and it just goes on and on. There's astronomy clubs out there, and they have telescopes which they love to share views during star parties. And so their websites often tell you when that's available. Of course, weather permitting. Otherwise, you're just going to see a planetary atmosphere, namely ours. Public observatory nights, the local institutions, scientific institutions, and colleges and universities do have observatories, and they do open them up for particular observing by the public. Harvard-Smithsonian Center for Astrophysics has every third Thursday for observing. This is, of course, once the pandemic is over, which is what we're in right now. Boston University, as I recall, was Wednesday nights. Wellesley, Merrimack College, Wheaton, on and on. Many of these educational institutions have observatories, which they're willing to share on particular nights, weather permitting. And finally, I'd like to note that Rockport, where I live, Rockport Community Observatory, is on its way. We've raised the necessary funds to house the 12-inch Meade telescope that we have, and also to have a heated control center. We expect groundbreaking in 2021, so very excited about that. Other experiential resources. There are some published activities and compiled together. The most recent is Learning Astronomy by Doing Astronomy, a collaborative lecture activities by Stacy Palin and Anna Larson. I would recommend this first. And I think it's in a notebook style so that you can actually take the sheets away to work on them. And then there's this big compilation by Andrew Fracknoy, Laboratory Activities for Astronomy 101 courses. So that would be at the college level, the intro college level. But this compilation has one of my favorite online interactives, which are hosted by the Nebraska Astronomy Applet Project. So this is very useful. Universe at Your Fingertips has been the Bible for K through 8 educators, and it's in its second iteration, available by DVD, also compiled by Andrew Fracknoy. And you may have your own favorites, and so I encourage you to let me know if you do. My email is williamhweller@gmail.com, and I would like to end by just reminding you that wisdom begins with wonder. So make sure that that's at the foremost in the front when you are engaging your students. Try to keep that wonder going. And then the obvious truism by Yogi Berra that you can observe a lot by watching. That is no truer than when it comes to astronomy. Sometimes all you have to do is look up. So with that, I thank you for your attention and wish you well. Take care. stop sharing. And